Now let's look at exercise 4.4.3. Draw 2 cards from a standard 52 card deck with replacement. Find the probability of getting at least 1 black card. Even though we're drawing cards from a standard 52 card deck, we want to look at the outcomes. So what are the outcomes that we are concerned about? Are we concerned about individual cards like the Queen of Spades or the Two of Hearts? Or are we concerned about the color? We're only concerned about the color in this case. So our outcomes consist of black cards or red cards. It doesn't matter that we have 52 cards in our deck. We're looking at black cards and red cards. We know in our 52 card deck that 26 cards are black and 26 cards are red. So we have an equal chance of drawing 1 black card or 1 red card if we're talking about one draw of the cards. So pulling 1 card out of the deck, the probability of drawing 1 black card is 1/2. The probability of drawing 1 red card is 1/2. Just a quick review from the basics of probability. Here, though, we have a different scenario. We're talking about drawing 2 cards from a standard 52 card deck. And when we draw it out, we look at it, we record what color it is, and we put it back in the deck. For our outcomes, we could write them as just 2 letters. Similarly to what we were doing when we were flipping 2 coins, heads, 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 tails, tails, heads, tails, tails. The same idea happens here. So for outcomes, we could have 2 reds, first card red, second card red, first card red, second card black, first card black, second card red, and both cards black. Now, at least 1, this is the probability we're looking for, the probability of at least 1 black. So looking at the outcomes, which ones have at least 1 black card? So at least 1 means 1 or 2. One or 2 black cards. We have 1 black card if it's the second card. We have 1 black card if it's the first card. And if we draw both of them black cards, we still have at least 1 black card. So probability of at least 1 black, our sample space S is what we just found. So we had 3 that had at least 1 black in our sample space out of 4 total. And so our probability would be 3/4. Example 4.4.4 says we're going to flip 2 fair coins and then find the probabilities of the events. So part A, the event F is getting at most 1 tail. So we either have 0 tails or we have 1 tail. Well, before we find F, we probably should write down, let's start over on this one too. In example 4.4.4, we're going to flip 2 fair coins and then find probabilities of some events that they're going to define for us. Let's start out, before we find those events, to determine our sample space. If we're flipping 2 fair coins, then the outcomes for the first coin are heads or tails. But the second coin coming in creates a new dynamic. The second coin, we could have heads, we could also have tails even if the first coin is heads. If the first coin is tails, we could have the second coin being heads or tails as well. Notice that this is very similar to the previous example with red cards and black cards. Red cards and black cards are equally likely, and we're pulling 2 of them with replacement. Here we have 2 fair coins that we're flipping, and one coin doesn't affect the other one. So again, we have these similar 4 outcomes as before. So here's our sample space: 2 heads, a head then a tail then a head, or 2 tails. And for part A, we want the event F to be getting at most 1 tail. So 0 tails or 1 tail. And looking at our sample space, 0 tails is the first outcome, heads, heads. 1 tail are the next 2. Tails for the second flip, or for the second coin, and tails for the first coin. And then if we want to calculate the probability of F, just like before, number of outcomes in F over number of outcomes in S, 3 in F, 1, 2, 3, and 4 in S. Our probability for event F is 3/4. For part B, G is the event of getting 2 faces that are the same. So here, 2 faces the same would mean we have 2 heads, or we have 2 tails. And the probability for G, still using that probability definition, number in the event divided by the number in the sample space. So we have sample space is the same, we still have 4. Here in G we have 2 outcomes. We can simplify to be 1/2. Part C says let H be the event of getting a head on the first flip, followed by a head or tail on the second flip. So we have a head on the first flip, a head on the second flip, or a head on the first flip, a tail on the second flip. And same idea, calculating probability of event H, number of outcomes in H over number of outcomes in S. S still has 4, nothing's changed for S. H, now we have 2, and probability of H is 1/2. Part D wants to know, are F and G mutually exclusive? So looking up here at F and at G, do they have anything in common? Do they have anything that's the same? They do. 2 events cannot be mutually exclusive. Mutually exclusive means they have nothing in common. But F and G both have 2 heads in common. So they cannot be mutually exclusive. And the last part in this example, let J be the event of getting all tails. Are J and H mutually exclusive? And again, we look at J, tails, tails, and we look at H, heads, 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 tails. Do they have common outcomes? Remember, outcomes in this instance is a pair of letters. So heads, heads is an outcome. Heads, tails is an outcome. Not just one heads, but the 2 letters together. It turns out that no, they don't. J and H are mutually exclusive. They have no outcomes in common. This also means that the probability of J and H is 0 because they have nothing in common.